this one. I will upload it online as well. When we talk about Bernoulli's equation, there are few important symbols. Friction losses represented by the HL, motor head losses, HM, pump head, HP. The unit of all these ones are the length. Z is the height. We don't use the H as a height because that is for these symbols. That's velocity, that's pressure, that's density. So rho or gamma, we use that one for density. Okay. Now, when we have a look at the Bernoulli's equation, we say total energy at the inlet should be same as total energy at the output, at the outlet. Now, energy comprises of various factors. It can be kinetic energy, it can be potential energy, it can be internal energy. Yeah. So if one energy change, if one decrease, the other will increase to equate, to make sure all the equations are equal. Multiple ways. There are 4 or 5 different ways of writing the Bernoulli's equation. One way is this: kinetic energy plus potential energy plus internal energy should at inlet. One is inlet, 1, 1, 1. So at inlet is same as kinetic energy plus potential energy plus internal energy at the outlet. That's one way of writing it down. Kinetic energy has a formula. Kinetic energy has a formula, half mv squared. I write down the formulas here. When we talk about the kinetic energy, it has a formula. It's half mv squared, where m is a mass and v is a velocity. Potential energy has a formula. It's mass times gravity times the height. Instead of writing h, we write z. Mass, gravity times the height. So if we want to have a look at kinetic energy, this is the formula. Yeah, we can divide everything by g, and we can have these formulas. You know, we can divide everything by g. We can have that formula. We're not looking into converting from one formula to another. We are just looking into how we can actually use the formula to find, to use this one to find the head losses, to find the inlet conditions and the outlet condition, or the missing inlet or outlet conditions. And this is what we are going to be doing that one today. Okay. Now, let's say we got, if I share my screen. Let's say we got this diagram, and here is the inlet, and then we got the outlet on this side. So the pump is here, then the valve is here. So this is the energy that's inputting into the system. And then the flow is from point 1 all across to point 2. So this is the energy that is received. Now this is the energy that will be delivered on the point 2. Between point 1 and 2, there will be some losses, some frictional losses, some head losses, some motor losses, some hydraulic losses. That will minimize the energy at that stage. But obviously we said you can't create energy, you cannot destroy energy. But because these losses mean because of friction, some of the energy, the flow energy or fluid energy will be converted into some other form of energy. And we need to actually consider the other form of energy, and that is the losses. The losses we actually accounted here on this side. Okay, so that's what we were looking into. Okay. Now let's have a look at some questions. Let's stop here. Okay, let's say we got a question where we got point 1 and we got a point 2. We want to actually calculate the work done to lift the water from point 1 and raise it all the way up to point 2. The difference between the height of point 1 and point 2 is 125 meters. The pressure at point 1 is 96 kilopascal, and the pressure at point 2 is 103.4 kilopascal. So this is the information given. You're also given the value of the density of the water, 9810, yeah, Newton per meter cube, that's relative one. And we also make an assumption that constant diameter of the pipe is being used. The diameter of the pipe, whatever is here, is the same on the other side. We also make assumption that there are 0 losses. Now, if the losses are 0, which means the flow rate has to be same. We also need to make an assumption that the water is non-compressible, incompressible fluid. The fluid is incompressible, and obviously there is no losses. So now what we need to do is we need to use a continuity equation. So we can use the continuity equation, which we know, and we know the Bernoulli's equation. So continuity equation, we use black. Which is flow rate at 1 is same as flow rate at 2. So A1, V1 is same as A2, V2. So we have that equation. We also have the energy equation. So the one equation I wrote here, so I'm just going to write down that one again. So P1 over gamma 1 plus V1 square over 2G plus Z1 equals plus HP should be equal to P2 gamma 2, okay, I write 2, but that doesn't matter, V2 square over 2G plus Z2, okay, plus HL. Okay. Now, because whatever goes in comes out, it's the same fluid. So I can actually call this one and this one, they're all the same. They have the same relative density, so I can get rid of that one. Now we are going to have a look at these equations and find the values. Now what we do is we use the Z1 as a datum line. What does that actually mean? The datum line means that we measure that's as a reference. So the Z1 is 0. So the Z1 here is 0. Z1 is 0. Z2 is 125 meters. Yeah, we have the P1 and we have the P2. We also have the diameter, but the diameter is D1 equals D2. Both diameters are same, which means the area of the pipe here is same as the area of the pipe on the other side. So we can actually use that bit. First thing we need to do is we need to find out the HP. So that's the first thing we are going to do. So we have the equation. One other thing, because as area 1 is also equal to area 2, for the condition of continuity, which means Q1 equals to Q2, the V1 should be same as V2. So velocity at 1 should be same as velocity at 2. Otherwise, you know, the equation will not work. if the velocity at 1 and velocity at 2 are equal, that means HL has to be 0. That's always the case. Now, I'm going to use the same equation, and I will actually, okay, because they are the same, I can call that one as V. V1 equals V2, I'm going to call that one V. Now, I will use the same equation on the top, and then I will see what else I can do. So I have the P1 as it is. I have the value. Okay. This one becomes a V square over 2G plus Z1. Z1 is 0. So we said Z1 is 0. So I'm just going to put a 0 here. Plus HP equals P2 over plus that becomes a V2 square over 2G plus Z2 is 125 plus HL. So HL, we said it's a 0. Plus a 0. So now I can simplify the equation a lot more because this thing is same on this side and it's same on this side. Sorry, that's 2 shouldn't be there. So I can cross these 2 bits. So the equation will become P1 plus HP plus 125. No, I missed the equal sign. Is the equal sign there? Now I can make the HP the subject. So the HP is equal P2 over gamma plus 125. I need to pick that one, move on. It's a positive here. When it move on that side, that becomes a negative. When I get that, I just need to put the values. So let's put the values and we get the answer. So P2 is 103. 103.4 kilo. And that value is 9810 plus 125 minus P1 is 96.5 kilo. 9810. So if you put that in calculator, you will get an answer for the HP. That will be in meters. So the answer will be in meters. It will be around 120 something. I got 125.7. Okay, to find the work done, because we got the HP. Now to find the work done, we got the W. Sorry, work done is that W is the weight actually. Weight times the distance, or the force times the distance. Yep. So that weight is going to be from here 9810, we assume it's 1 meter cube. So that's the force required to lift it, multiplied by the distance moved, 125.7. Whatever you do that one, the answer, whatever the answer is, that's going to be in joules. Yeah. So that will be the answer for this bit. Now let's say we got a question where the water is flowing into a turbine, and it's generating the power. The diameter of the pipe that we are using is 100 millimeter. The flow rate is 0.01 meter cube per second. The pressure at the inlet is 1000 kilopascal. The pressure at the outlet is 500 kilopascal. The difference of the height is 30 meters. If we increase the height, we can get different power here, considering the pressure is the same. Okay, we have to assume there's a water system flowing through the system. So we assume the density of the water as 1000 kilogram per meter cube. We also assume there are zero losses due to the friction. So there are no losses, and we also make an assumption that the liquid water which using, we cannot compress the water. So we make that assumption, which means the equation of continuity A1 V1 equals A2 V2 applies, which also means the energy equations, the Bernoulli's energy equation applies. Now there is a one new formula for the power. The power formula is which we are going to be using. It's P equals H, like which are the losses, yeah, or the head, the turbine head, HT, multiply by how much is the flow rate, multiply by the relative density. So we got that bit. Now, if we use the energy equation, let me write down the energy equation. I got the energy equation as P1 over so that remains the same all across. So plus Z1. Okay, let me just leave a little bit space and let me write this one. Okay, so I got that bit. Now here I will have, and here I will have, we need to do one, we need to make one assumption here. We have the formula for the power one on the top. Yeah. Now, because the equation of the continuity applies and the G is constant, if the continuity equations apply, the V1 should be equal to the V2. So the V1 and the V2 are equal, which means I can get rid of this and I can get rid of that. Which means if they both equal, I can simply cross that one and I can simply cross that one. Now Z1 is 0. This is Z1 and that is Z2 all the way here. That's Z2. So Z1 equals 0 and Z2 is 30. So if I put Z1 is 0, Z2 is 30 meters. So I can just put the value. Now also there are no losses. So HL is going to be 0 because there are no losses. That thing will be 0. Now the HP is what we're trying to actually work out. we will try to make this one, and we'll try to arrange the equation and make the HP the subject. To make the HP the subject, let's rearrange the equation. Okay, the HP equals P2 minus P1. Okay, that becomes 0 already. And that becomes a 0 already. Plus Z2. Yeah, that's it. I got this one, I got that one, and I got Z2. Yeah, that's it. So I got this one. If I can simplify the equation, I can call that one HP. If I can take this one common, I got that's Z2. So this is my equation. Okay. Now I can put in the values and then I can get the answer. Now HP is same as HT. So I just replace this value with HT. Now let's put the values. The values we are putting in kilo. So the answer will be, we need to convert that one into normal. So P2 is 500 kilo. 500 and then kilo, 10 to the 3 minus kilo over, we have the value. So what's the value of the density we got? That's given to us. Yeah. So the density is given. Now we have to convert that density into the force. So we need to multiply that by 9.81 gravity factor, or 9.8, doesn't matter. Yeah. Plus this is 30. Distance from here all the way to there. That will give us the HT value. Anyone with an HT value? Okay. Now, because it's the height, it's the length. So this one can never be, this one in the bracket can never be negative. So this has to be a positive. So because this has to be positive, I put under the mod. Other way of doing that one is make sure you do the bigger pressure minus the lower pressure. Yeah, if you do that way, you will always get that right. But because I've used the same equation, so yeah, doesn't matter. So I got whatever the answer here is, minus 50, make that positive because height can't be negative. Yeah, and you can see it's going down. So you got minus 50.97 plus 30. So 50.97 plus 30, that is 80.97. Now, once we got the 80.97, I want to find out the power generated by this, the power generated by this thing. So we have the formula for the power. P equals to the HT times by Q times by the relative density. So I got HT, I got 80. I just put in the values. So this is 80.97. The flow rate is given here, 0.01. Okay. Now the value here, the value for that one, the density of the is 1000. We need to convert this density into the relative density. So that will be 1000 multiply 9.81. Yeah, which is that value. So if you do that one, The answer you will get is in kilowatts or watts. So you need to write down that one either in kilowatts or watts. Anyone got an answer?
7943.57.
So, or you can write down 7.9 kilowatts. So this is the power generated by this turbine.